Alright guys, welcome back to the channel. We're going to be solving question 55 from the first chapter of the Johnston textbook, Mechanics of Materials. And in the structure shown, an 8mm diameter pin is used at point A. So we have three different views of this structure. We have the top view on top, front view, and side view on the right hand side. So we know that the pin at point A here is 8mm, and also we have the diameter of the pin at point B. That would be 12mm. We know that the ultimate shearing stress is 100 megapascal at all connections, and the ultimate normal stress is 250 in each of the two links joining at B and D. So we have these two joints, these two links, and we need to determine the allowable load P if the overall factor of safety in this structure is 3. So we are dealing with three different things. We have two pins at point A and also point B, which has shear stress of 100 megapascal. We also have ultimate normal stress of 250 in the link BD in here, that we need to check for the force, or we actually need to find the force P based on each of these three conditions. After all, we're going to go with the lowest P, because that way we can make sure that that force P is not going to compromise any components of this structure. So before we start, we are dealing with the force at point A and force at point B. So I'm going to start with the free body diagram of this part of the beam here. If we just want to draw the free body diagram for that one, I'm just going to show it in here just to avoid having the, so I'm drawing the free body diagram for ABC. So we have a pin at point A, which means we need to consider both AX and AY, and AY is actually the force that can make shear stress on the pin at point A. And let's consider another force for B in here, BY. And you might say that we need to consider one X component for joint B2, but like the reason for BY that I don't consider any X component is that at BD we have a two force member, which means the force that is applying from the link BD to the ABC would be along the line that connects these two. So it's either like that or in the opposite direction. So we know that the force that is applying from the link to this joint is in Y direction. So that's why I don't consider any X component in here. And again, it's coming from the concept of two force member. When we have a link that we only have force at two ends, the resultant of force would be along the line that connects these two. So this would be the force that we have. It's just we have a vertical force in here. And the last force is the force P at the other end, and we're going to consider our equilibrium equation. Sum of all forces in X equals 0. That means our AX is 0. And what we are interested in here is the force in BY, because that way we can deal with the shear stress on the pin at point B and the normal stress on the link BD. And for A, we also have another pin at A, so we need to deal with the force at point A. So what we're going to do is that we need to get rid of one of these unknowns in here. And since we are in equilibrium, we have sum of all forces equals 0 and sum of all moments about any point that we want to. So let's start with the moment about point A, counterclockwise positive as always. And if we do that, we can get rid of all the unknowns at point A, and we can find By based on P. So let's do that. We have all the dimensions in here. We know from A to B. Here we have 200 millimeters. And from B to P, if we look at it, it will be 180. So we have the moment of By. Since it's in this direction, it will be counterclockwise. So positive By times the distance is 200 millimeter divided by 1000 in order to get it meter. So 0.2 meter. And the moment of P would be clockwise. So we have a negative sign, P times, this time we have 200 plus 180, which is going to be 380 or 0.38 meter. This will be equal to 0, so we can find P based on BD. So P will be BY 0.2 divided 0.38 times BY. So that's that. And if we do the sum of all moments about point B, we should be able to find A. So this time we're going to have the moment of AY. Since we consider clockwise moment, we have a negative sign in here, AY times the distance from A to B, which is 200. So 0.2, again, in order to get it in meter, we're going to divide it by 1,000. And also moment of P is clockwise as well about B, so this will be also negative. That shows that our assumption for AY was not correct, and AY is actually downward because we get a negative sign for AY. So that's going to be P times 180 divided by 1,000, or 0.18 equals 0. And as I mentioned, our P in here based on AY would be negative 0.2 divided by 0.18 times P times AY. And again, it shows that AY has to be actually upward instead of has to be downward, and our assumption was not correct. So now we have AY and BY based on P. So if we can find AY and BY, since we have the factor of safety, we should be good to find the P in each of these scenarios. Let's start with the shear in pin A. So we have factor of safety equal to the force A, the ultimate force of AY over AY. And since we have the ultimate shear, we gonna have the ultimate force over the area. So this is AY. And the area that we are dealing with, let's start with the A. So if we look at this figure, we see that the area that we have is the area of the pin, which would be this cylinder that's going to get cut at two areas, one in here and one in here. So we are dealing with two areas. So I'm talking about these two areas, which is these two shaded area that I'm showing. So the area that we are dealing with in here would be 2 times the area of each of those circles, pi divided by 4, and we need the diameter. If we get back to the question, we have the diameter of A 8 millimeters. So we're going to divide it by 1,000 in order to get it in meters squared. So that's going to give us meters squared. So the ultimate force at A, that's what we're looking for. And the ultimate shear, we have this as a given in the question too, will be all the shearing stress is 100 megapascals. So this will be equal to 100 times 10 to the 6 Pascal. That should give us the force in newtons. So we also know the factor of safety in this question is 3. If you get back to the end of the question, it says that the factor of safety is 3. So based on this, here, our AY would be simply the ultimate force divided by 3. So the ultimate force in here would be just, if we cross multiply these, we're going to get 100 times 10 to the 6 times 2 times pi over 4, 0.008 squared divided by 3 is going to give us the AY. Let's calculate this. 10 to the 8 times 2 times pi times 2 times pi times 0.008 squared divided by 12. So that would be our AY, 3,351.03 newtons, and we know that our P is equal to what we found in the previous step for AY, And here we're looking for the absolute value. The negative sign is because we picked the wrong direction, so that's why we have a negative sign. We don't need to consider that negative sign in here. So our P would be 0.2 divided by 0.18 times 3351.03. So basically in here we just need to multiply this by 0.2 and divide it by 0.18. And the P that we're gonna get would be, if we just report it in kilonewton, 3.723 kilonewtons. So that was based on the shear in pin A. Let's move on to the shear in pin B. And we're gonna have the same scenario. If we just combine all of our equations, our By would be basically the ultimate shear stress times A divided by 3. Keep in mind our area. So again, we have 100 times 10 to the 6 Pascal. That's the ultimate shear stress. It's the same. Pi over 4. Again, we're going to have the same scenario for the area of the pin B. If we look at B, it will be the same. So this time we will have another pin that it would undergo shearing stress at these two areas. We just have a different diameter for pin B, so it's 12 instead of 8. So here we're gonna do again times 2, and the diameter would be 0.012 squared divided by 3. Let's calculate this. We can find our By, and after that we can find P. So 10 to the 8 times pi times 2 times 0.012 squared divided by 12. That's gonna be 7,539.8 Newton. And if we want to find P, let's get back to our P. So this is our P based on By, 0.2 divided by 0.38 times 75039.8. So let's just multiply this by 0.2 divided by 0.38. That's gonna be, if you divide it by 1,000, it will be 3.97 kilonewtons. And this is our second P. The first P was 3.72, and this one is 97. So far, this is our winner. But we have one more thing to check, and that would be the normal stress on in link BD. So first of all, about the direction, if we get back to our free body diagram, so By, the direction for By was correct. So that means the link BD will be in compression, because this is the force from the link to the joint. So the force from joint to the link would be in the opposite direction. So the link will be in compression. So the normal stress that we're talking about in here is compression. So if it's in compression, the area that we are dealing with, as we discussed in the previous questions in this chapter, will be the area of the center of this link. And if it was in tension, it would be the area where these two pins are located. But that's not the case. We are in compression, and the area that we have would be the cross section of that part, which will be somewhere in here. And again, as we can see, we'll cross it into two links. And what we are dealing with is two different rectangles, 1 and 2. And if we want to find the dimensions, we have 8. As we can see, the thickness in here is 8. And since it's 3D, it will be something like that in here. And the other side would be the 20 millimeter that we can see in the front view. So 20 millimeter. So for the area, basically we have 2 times 8 times 20. So let's go to the last part. This time we're going to go with the compression in links, and the links of the two BD links that we were talking about. And it's going to be the same thing. This time, instead of shearing stress, we have normal stress. So same thing. The force that we are dealing with is again the force that we have at B. So we need the ultimate By over our By, and the ultimate By would be again the ultimate strength times the area. For the area, again, we are dealing with two of those rectangles, so keep in mind that would be our By. So our By would be basically this. So let's check out what was the normal stress. The normal stress this time would be 250. So 250 megapascal times 10 to the 6 in order to get it in Pascal. And the area, we have two of those rectangles. It was 20 by 80. So we have 20 times 8, which will be 160. And since that's in millimeter, we're going to do 10 to the minus 6 to get it in meter. And we're going to divide that by 3. And that's going to give us the By. Let's calculate that. So 250 times 10 to the 6. Actually, these two will be canceled out, so we don't even need to multiply by that. Times 2 times 160 divided by 3. So that's going to be 26.667 kilonewtons. So our P in here would be same as previous part, since we are dealing with By, 0.2 divided by 0.38, 667 divided by 0.38, and that's gonna be 14.04 kilonewtons, and that would be the last force P that we get. And as I mentioned, the final answer would be the lowest P, because that way we can make sure that it's not going to compromise any parts of this structure. So we have 3.72, which is lower than this, 3.97, and it's lower than 14. So our final answer would be 3.72 kilonewtons. And yeah, that's pretty much everything for this one. Hope everything was clear. Let me know if you guys have any questions. And you guys take care. I'll see you in the next video. Have a good one.